Hey guys, welcome to Safi Mixed. In this video, I will try to lay down the foundation for understanding Laplace transform and will introduce the definition of Laplace transform. In theoretical sciences, we use different transforms to find the solutions of different equations, whether algebraic or differential. For example, you have already used a transform, you have learned how to use a transform from your school level mathematics, and that is the logarithmic transform. The logarithmic transform the product of two series or of two numbers of any of two functions to the sum, to the logarithm of the sum of two functions. Similarly, the logarithmic transform converts the fraction of two functions, the fraction of two series, the fraction of two very large numbers into the difference of the logarithmic of those two entities. That is, we know that if we take this thing log of S1 and S2, where S1 and S2 could be two functions, could be two series, or could be any two large numbers, we can write this in the form of the sum of S1 plus log S2. And obviously, we use other information of the logarithm. For example, we can use the logarithm to be natural with base e, could be with base 10, could be with base 2. So if you are using with base 10, that means you are dealing with decimals. If you are using base 2, you are dealing with binaries. So those are the different fruits. And we have also have this thing log of S1 over log of S2 equals log of S1 minus log of S2. So this is what you learn in your school level mathematics, how to use a transform to convert the products into sums, the fractions into difference. And you have probably learned about another very important transform we call Fourier transform, in which a periodic function is converted into the sum of trigonometric series. Similarly, we in science, and particularly in theoretical science, we deal with differential equations that describe the dynamics of certain physical quantities with respect to certain other set of physical variables. So, in order to find solutions of such equations, we use different techniques. And the Laplace transform is one of the powerful tools for the solutions of those differential equations. In fact, the Laplace transform is a wonderful tool based on the rules of integration to find the solution of ordinary differential equations and of partial differential equations with constant coefficients. So with that in mind, let me introduce the mathematical definition of Laplace transform for a function. I consider a function if in the form of f of t, where t is a variable describing the dynamics of the function or the shape of the function. For most of the theoretical problem of physics, this t is usually time, but that could be any variable. Then the Laplace transform of this function, we write it like this. We use this scripted L, and inside the square bracket, we write the function, and then we write an integral from 0 to infinity, write an exponent with argument s and t, multiply this with the function t, and integrate this integral over t. And sometimes we put this integral into another form, limit ta tends to integral from 0 to ta exponent minus st f of t dt. In this form, we first find the integral, solve the integral, and at the end result, we put the limit. And when this limit exists, we say the integral converge and the function possesses Laplace transform. And if the limit does not exist, we say the function f of t does not have Laplace transform. So it is important to note that not all the mathematical functions possess Laplace transform. It is not necessary. So not all the mathematical functions possess Laplace transform. Now, t in this relation is real and is greater than 0. S could be real or complex. It has different forms, different domains for different problems, for different differential equations, for different functions. So if t is time, then we know that the argument of exponential function is dimensionless. This is important. If you don't know about it, you should note this. The argument of exponential functions is dimensionless. So if t is time, then obviously for this argument to be dimensionless, s must be frequency. So this is in fact the basic definition of Laplace transform that we use for the solutions of differential equations and ordinary differential equations. So now what's the procedure? In fact, it is a three-step procedure. First, through this one definition, we transform the differential equation into an algebraic equation. That is the first step. Then we use the rules of algebra to find the solution of that algebraic equation. This is the second step. And if that is finding the solution of the algebraic equation is the second step in the procedure of finding the solution of differential equation through Laplace transform. And number three, the result of the algebraic equation is retransformed to find the solution of the original differential equations. So in order to use the Laplace transform, you need to go through three steps. First, find the Laplace transform. First, convert the differential equation into algebraic. Then solve the algebraic equation, and then retransform the result into the solution of original differential equations. Thanks for watching.